Hi everyone, my name is Justin Baraboo, and today I'm going to be talking about the project I did for the EECS 395 course at Northwestern of optimization for deep learning. For this project, I'm looking at the ICIAR challenge that one of my colleagues, Haben Burhan, wrote a DenseNet CNN for to enter the challenge, and I'm going to be looking at optimizing that. The data that we see here is breast cancer histology slides, where there were 4 major classes of normal, benign, in situ carcinoma and invasive carcinoma, which we reduced to just 2 of being normal and invasive. And as you can see, since we're using a DenseNet CNN, we're going to be working with both the entire image itself, but also local patches, which you can see on the right. And we're going to be trying to train the neural network to be able to discriminate between these classes and optimizing it so it can do that better. So to get into the meat and the bones of our optimization pathway that we're going to be investigating, I really only looked at momentum optimizers and only really looked at first order optimizers, which we saw in class really looks at the gradient of the cost function in order to make decisions of where it should go. The ones that I looked into are Nesterov momentum, Adagrad momentum, and Adam momentum, which if you want to see the differences between these and how they differ from classical momentum, you can see it in the project text main. But the big idea is that Nesterov is going to have a gambling type of choice that's going to correct, where Adagrad is going to look at previous gradients of single parameters, squaring them, and then using that to make decisions on where it should move. And then Adam is really going to be looking for very flat local minimums spaces. And then within these momentum optimizer classes, we're going to be looking at how the learning rate affects the optimization, regularization affects it, and how batch optimization affects it. Usually in class, we used the cost function itself as a way to determine whether or not a machine learning technique was good or performing better. But here we're going to be using loss as our metric of comparison because it also takes into account the fitting of the high capacity model since we're using a neural network. Just real quick before we jump into the results, I want to talk about the Jupyter Notebook design to help you better investigate it and see how everything flows. The main place you want to look is the project text main, which is going to talk about these different momentum optimizers and the pathway that I use them in, as well as their other initial configurations and the parameters that I used. The project data notebook basically does the patching and converts the files to be able to be read by the TensorFlow workflow that Haben designed. And then finally, the real thing that's actually performing the machine learning and its optimization is in the breast history CNN Jupyter Notebook, which is utilizing both a data provider and initial config file. And there you can see some of the runs that I did with different parameters and regularizations and learning rates and see that. But all that information from the Brehas CNN is also in the project text main. So just reading the project text main will tell you the entirety of the project, where if you want to look and see specific code, you can look in the Brehas CNN. So the first thing we're going to do is look at the learning rates. And the thing to know about what I did is that I only looked at 2 epochs of data with a checkpoint in between the first and second epoch in order to reduce the amount of time that I was actually running this, as it would take about an hour and an hour and a half for each of these to run. And what we see here isn't really too surprising, as the smaller learning rates tended to do better than the bigger learning rate for all of the optimizations, where the smallest one, a 0.001 learning rate, did best for Adagrad and Adam, and the 0.01 actually did better for Nesterov, though it's fairly comparable. And longer epochs would definitely see a difference as it converges better. But then these learning rates that I found were then used to find a regularization rate. So after determining the learning rate from the previous slide, we can see the different regularization rates that I tried, 0.001, 0.001, 0.01, and 0.1. Here we see that the higher regularization, so the more smoothings, had a better effect, with the highest regularization being the best for Adam and the 0.01 being the best for Adagrad and Nesterov. So here we can see like the first surprising thing of this project is that when comparing full batch to half batch processing here, I found that the full batch actually worked better than the half batch using the learning rate and regularization parameters that we found above, which were again found with full batch. So maybe a different set of learning rates and organizations could make half batch better as we would expect, especially across the limited number of epochs, as the training time for the half batch was actually a lot longer, taking maybe about 2 hours on my machine for each one of these. So to conclude, this project was really good for me for applying modern ways of doing optimization as well as different parameter tunings such as learning rate and regularization of batch processing to a modern state-of-the-art neural network and actually applying that as in class we did a lot of demos for understanding the mechanics of basic things, but here this really let me solidify how it is to apply it to actual CNN.